Okay, so we have introduced two different criteria. The minimization of the mean-square error, which is a very well-known criterion in parameter estimation, and in particular, people should be familiar with the linear minimum mean-square error estimator, whose solution is typically called Wiener filter. And the second criteria, which is also very widely adopted for detection problems, which is the maximization of the signal-to-noise ratio. In this case, the maximization at the output of the beamformer. So we want to design the beamformer that maximizes the signal-to-noise ratio after spatial filtering. And we discovered that to maximize the signal-to-noise ratio at the output of the beamformer is equivalent to maximize the array gain. So the improvement in terms of signal-to-noise ratio from the output, from the input to the output. Okay, so we want to find H that maximize this ratio. Now, H is both at the numerator and at the denominator. So, we could do two different things. We could try to keep constant the denominator and maximize the numerator, or the reverse. We can try to keep constant the numerator, and this is called distortionless constraint. So we want that the signal of interest passes undistorted through the beamformer. So to keep constant the numerator is equivalent to impose a distortionless constraint for the signal of interest. So we keep constant the numerator and we minimize the denominator. So we minimize the interference that passes through the side lobe of the beamformer. And typically, we apply this second approach. So we try to minimize the denominator while keeping constant the numerator. So this is the way we will solve this optimization problem. So in other words, the problem can be restated in this way. So we want to find the optimal beamformer from the point of view of the output signal to interference plus noise ratio by minimizing the output, the power of the output of the interference subject to a distortionless constraint that in this case is expressed in this way. Now, how do we solve this problem? We can use the Lagrange multiplier method again. Now, this quantity is real, so the constraint can be expressed in this way without the conjugate. So this is the function that we need to minimize. Lambda is the Lagrange multiplier. We calculate the gradient. So trust me that this is the gradient of the quadratic form Q. We set the gradient equal to 0, and we obtain the linear system of equations that we have to solve. Now, if Rs were not present this would be a classical eigenvector problem. Because of the presence of RS, this is a more difficult problem to be solved, and it is called generalized eigenvector problem. So it's a sort of generalization of the well-known EVD problem. So we have to solve this problem. Now remember that the optimal H should satisfy the distortionless constraint. So if we multiply on the left by H Hermitian, this relationship becomes H Hermitian RWH equal lambda H Hermitian RSH. But because of the constraint, this should be 1, and so this is lambda. So in other words, the quantity that we want to minimize, which is the left-hand side, should be equal to 1 of the eigenvalues of this generalized eigenvector problem. And if we want to minimize this, lambda should be the minimal eigenvalue. The minimal eigenvalue of what is called matrix pencil, so which is the couple of these two matrices. So in other words, lambda, the Lagrange multiplier, should be the minimum eigenvalue for this generalized eigenvector problem. And in MATLAB, you can find subroutine to solve this problem. So you find the eigenvector associated to the minimal eigenvalue, and that is the solution that you are looking for. If the disturbance correlation matrix is full rank, and typically it is, at least because of the presence of white thermal noise, if the disturbance correlation matrix is full rank, again, if you look at this relationship, you can multiply on the left by the inverse of RW, and so you get this problem. Now you can bring lambda on the left-hand side. So in the case where RW is full rank, you can rewrite this equation in this form. And this is now the classical eigenvector problem. And so if lambda should be minimal, 1 over lambda should be maximal. And so the solution H, the optimal H, is what? Is the eigenvector associated to the maximal eigenvalue of this matrix RW, inverse of RW times RS. So this is typically called, so the eigenvector associated to the maximal eigenvalue is called principal eigenvector. So the optimal beamformer from the point of view of the signal to interference plus noise ratio is the principal eigenvector of this matrix. So okay, so we can transform a generalized eigenvector problem, which is the one that we have to solve, into a classical eigenvector problem if, only if, the disturbance covariance matrix is full rank, so it can be inverted. And this is the solution. And actually, this solution does not rely on the assumption that the signal is a point-like signal. So it does not rely on the assumption that RS has the classical rank 1 structure. So this is the optimal beamformer, whatever is the structure of the signal correlation matrix. So if you have, for example, spatially spread sources that you remember how we derive the covariance matrix of the signal in the presence of spread sources. We introduce the speckle, blah, blah, blah. So for that case, you can find the optimal beamformer in this way. Now, let's assume that there is only one target or one source, and this source is point light. So the same assumption that we made to solve the first problem, so the minimization of the mean-square error. So let's assume that the signal vector has the usual expression for a single point light source. So it is the array response calculated at the directional arrival of the signal, theta t, that multiplies the signal generated by the source. What is RS in this case? Okay, we calculate, it's the usual rank 1 matrix. And so, if you make the replacement of this RS here in the constraint, so what you get is that the constraint becomes the modulo square of this quantity equal to 1. Or you can say H Hermitian A equal to 1, which is exactly the same constraint that we applied to find the classical beamformer, if you remember. So in this case, so if you write H Hermitian A equal to 1, you can again find the solution by using the Lagrange method. There is only one small difference between this functional Q and the one that we solved to find the classical beamformer. And it is the fact that to find the classical beamformer, here we have Ry. So the covariance matrix of the observed signal. So signal of interest plus disturbance. Here we have only disturbance. So this is a small but very, very important difference. And I will comment on what is the implication of this difference, okay? But if you go back to chapter 2 and you compare the two problems that we solved, there is this small but very important difference. Okay, the solution is found in the usual way. So you calculate the gradient, you set the gradient equal to 0, you find the solution, and then you impose the constraint to find the Lagrange multiplier, and you get the solution. And this is the solution. Now, this denominator is a scalar, but it is irrelevant because, I mean, whatever is the constant in front of this term here, the beamformer is optimal because this constant, the value of this constant that I call K, does not affect the signal-to-noise ratio because it changes its scale in the same way, the power of the signal and the power of the noise, and the ratio remains unaffected. And this solution, again, is not the meshed filter, so it's not proportional to A because of the presence of this matrix. Now, if you compare the two solutions, they are slightly different. So the optimal solution from the point of view of the minimization of the mean-square error is proportional to the inverse of the data covariance matrix times the array response calculated at the steering direction. Instead, the beamformer, which is optimal from the point of view of the maximization of the signal to interference noise ratio, is proportional to the product between the inverse of the disturbance covariance matrix that multiplies the array response. So there is this very important difference. Ry includes Rw, but includes also the signal contribution. And the signal contribution, in the case of a single point-like source, has this well-known structure. Now, apparently they are different, and there are differences very important that I will stress in practice later on. But before showing the different behavior of the two, let me stress one thing. First of all, it's clear that we cannot implement neither the first one nor the second one, because typically we don't know Ry, we don't know Rw. So they should be estimated from the data. Now, we have seen how to estimate Rw by using n snapshot. But typically this n snapshot contains also the signal. So if you want to estimate Rw, so if you want to estimate this, so we know how to estimate this, we have already seen. The problem is that if you want to estimate this, obviously we can use the sample covariance matrix, but we need to observe, to collect snapshots that are signal-free, that contains only disturbance. So what we call signal-free secondary data. In passive sensing application, this is more difficult to achieve, to have. In active radar, this is possible, and typically signal-free secondary data are obtained from adjacent range cell adjacent to the cell under test. So you collect data from other range cells under the assumption that the noise, the disturbance is stationary in time and space, and so the secondary data share the same correlation structure as the cell under test. And this is the way we do in radar. So in active radar. In passive sensing, passive sonar, passive radar, this is typically not possible because you don't have the availability of range cells free of signal. So you can be, let's say, forced to use one or the other depending on the particular scenario. So, but it's important that you understand the difference between the two. Now, it can be proved that if we know exactly the two matrices, and I repeat, this is an ideal assumption. In reality, they are unknown. But if we know exactly Ry and Rw, and we steer the beam in the direction of arrival of the single point-like target, so we steer the beam to theta t, it can be proved that the two beamformers coincide. Why? Let's see how to prove this, okay? So we have a single point-like target. So the structure of the signal covariance matrix is this one. So we have to calculate the inverse of Ry, so the inverse of this matrix, times the array response. Now, this is a rank 1 matrix, and this is a typically full rank matrix. Now, the inverse of the sum can be expressed in this way by using a well-known result in matrix theory, which is called matrix inversion lemma. There are many forms of the matrix inversion lemma, and one of them is called Woodbury identity. So if you search in Wikipedia matrix inversion lemma or Woodbury identity, you find this identity. So the inverse of the sum is equal to this. Then you multiply by A, so you get RW inverse A minus, when you multiply this by A, you get this, okay? Now you can put this in evidence because you have this term here and here. So you have 1 minus this constant. This is a scalar, this is a constant, because A Hermitian RW to minus 1, A is a scalar, and the same, the denominator is a scalar. So this term in matrix is a scalar. So in other words, the optimal MMSE beamformer is a scalar version of the optimal SINR beamformer. So the difference is only the scalar alpha. But the coefficient alpha is immaterial in the sense that it does not affect the performance. It does not affect the output signal to noise ratio. And so this proves that the two beamformers are equivalent, but only if the two matrices are perfectly known. So in other words, they are equivalent only when the number of snapshots tends to infinity. Because only when the number n of snapshot tends to infinity, the sample covariance matrix estimate tends to the true covariance matrix. So in other words, they are equivalent, but only asymptotically, when the number of snapshot tends to infinity. Now, let's call this beamformer. So now we understood that asymptotically they are the same. So let's call this unrealistic beamformer, let's call this clairvoyant. So clairvoyant because it's the beamformer that knows the two covariance matrices. And this is the optimal beamformer for both criteria: minimization of the mean square error and maximization of the signal to noise ratio. So this is a clairvoyant optimal beamformer. Obviously, it cannot be implemented in practice, but the performance of this beamformer basically represents a benchmark to the performance that can be achieved by any adaptive beamformer that is obtained by replacing this or this by their sample covariance matrix, so by their estimate. So to analyze the performance of the clairvoyant optimal beamformer is important because it provides the best possible performance that we can achieve. We cannot go above that. And actually, these are the performance to which our adaptive beamformer will tend when the number of snapshots tends to infinity. So when the estimates tends to be better and better. Let's derive the array gain now. The array gain of the optimal beamformer. Okay. So in the case of, so this is the, we derive this. This is the expression of the output signal to noise ratio for any beamformer H. And we can express in this way. This ratio is the input signal to noise ratio. Now, if the source is point-like, this numerator becomes this one. So we have only one single point-like source. So this is general. This is valid also for spread sources. This is valid only for a single point-like source, okay? So we can express this numerator as the modulo square of A Hermitian A. Now, this is in general for any H. Now, if you calculate this for the optimal clairvoyant beamformer, we find the maximum output signal to noise ratio that we can achieve. So we replace H with the optimal H, which is A Hermitian RW. So this is the Hermitian of optimal H. Obviously, I mean, the scalar alpha cancels out because you have alpha square at the numerator, you have alpha square at the denominator. So as I said, alpha is irrelevant. It cancels out. So you have the numerator is the modulo square of A Hermitian inverse of RWA, and this is the denominator. But if you remember, RW is the total power of the noise that multiplies the normalized correlation matrix Q. So if you make this replacement here, you simplify, because here you have the modulo square. At the denominator, basically you have exactly the term of which you calculate the modulo square, but this quantity is real, so you don't need the modulo square. You simplify, you get this. So the array gain of the optimal clairvoyant beamformer is this term here. A Hermitian Q to minus 1 A. Okay. Now, let's assume that we have just an example. So let's calculate the array gain. In the case where in the disturbance, we have one jammer and white noise, so uncorrelated noise. So this is the general expression of Q that we derive in the presence of one jammer with JNR. JNR, remember, is the jammer to noise ratio. So it's the ratio between the power of the jammer to the power of the noise. So the jammer is directional. So Qj is A theta j, A Hermitian theta j. And if the noise is white, this is the identity matrix. So this is the expression of Q in the case we have in the disturbance one directional jammer plus white tones. So we make this replacement. So we replace Q here. So we have A Hermitian, and then we have the inverse of this. And then we multiply by A. Again, we should calculate the inverse of a rank 1 matrix plus a full rank matrix, in this case, plus the identity matrix. And the inverse of this by the Woodbury identity can be expressed in this way. So first, I bring outside this constant. So what remains is this one. So it's our rank 1 matrix plus 1 divided by J and R, the identity matrix, and then the inverse. Now, this inverse here can be very easily calculated by using the Woodbury identity. This is what we get. And then we multiply on the left by A Hermitian, on the right by A. So we do this multiplication. So what we get is the following. A Hermitian, J and R, I, A, this is equal to M. Is equal to M because it is the energy of vector A, which is equal to M. This product here, A Hermitian, A theta J, is the inner product between the ray response calculated in the steered direction and in the jammer direction. Now, we can assume that if the steered direction, theta t, which is also the directional arrival of the source, and the jammer, if the difference is greater than the beam width, basically this inner product is zero. So it's like you multiply two sinc functions that are shifted enough. So when you multiply, the overlap is only in the side lobes, and so the result of the product is negligible, it's almost zero. So this second term disappears, and this is the result. So the array gain is the jammer to noise ratio plus 1 multiplied by M. So we find a very interesting result. And this result says that the array gain is proportional to the number of sensors. So if you start from data that has a very low signal to noise ratio, by using beamforming, you can improve the signal to noise ratio. How much you improve is determined by the array gain. And the array gain depends on the covariance matrix of the signal, the covariance matrix of the noise, and the maximum improvement, which is guaranteed by the clairvoyant optimal beamformer. In this scenario, where you have a single point-like source, a directional jammer, and white noise, in this scenario, the array gain is proportional to the number of sensors. So you can increase the array gain by increasing the number of sensors. Obviously, to increase the number of sensors, you have to put more money on the hardware. So nothing comes for free. But it's important that you know that if you are willing to pay, you can increase theoretically as much as you want the signal to noise ratio by increasing the size of the array, by increasing the number of elements of the array. So for example, if you have 10 sensors, if you have a jammer with jammer to noise ratio 10 dB, and if you start from a signal to noise ratio of 10 dB, the signal to noise ratio that you can achieve, the maximal signal to noise ratio that you can achieve at the output of the array is 30 dB. If it is not enough, you have to increase the number of sensors. So can you understand well what I'm saying? So is my terrible English good enough to understand? Badri, I'm asking you because apparently the student do not answer my question. So are you still alive? So can someone give me a sign of life?
Yes, sir. You are audible, sir.
Thank you, because it's quite difficult to teach something and I don't see your faces. So it's difficult to understand if you can follow me or not. Okay, let's go ahead. So we derive another beamformer. Still, it is not adaptive. Okay, so we will make it adaptive. But for the time being, we can say that we know how to design the classical beamformer, and we know how to design the optimal clairvoyant beamformer, which is optimal both from the point of view of the minimization of the mean square error and the maximization of the array gain, or maximization of the signal-to-noise ratio at the output. What is the relationship between the two? It's important to understand the relationship. Okay, let's go back to the classical beamformer. The classical beamformer is nothing but a matched filter, because the observed vector y is proportional, and the proportionality parameter is S of n, so is proportional to this vector. And this vector is what? Is the array response calculated at the directional arrival of the source, plus noise. So the classical beamformer is proportional to A, to the array response. Again, the constant is immaterial. When we derive, the constant was set equal to 1 over m, but you can put any value in place of 1 over m. So the classical beamformer is nothing but the matched filter. But remember, the matched filter maximizes the signal-to-noise ratio only if the disturbance is wide. But sometimes the disturbance is not wide, because you have clutter. In sonar application, you have reverberation, or you may have interference, which is typically directional. So in radar, we call this interference jammer. So most of the time, the disturbance is not wide. And so the matched filter is not optimal. What is the optimal filter? The optimal filter is what we derived previously. So for example, if you consider the maximum SINR criterion, the optimal clairvoyant beamformer is the inverse of the disturbance covariance matrix that multiplies the array response. Or, I mean, you can write RW as sigma W squared times Q. And so you can express the optimal clairvoyant beamformer in this way. Is one constant, for example, 1 over m. Then we have the inverse of the normalized disturbance correlation matrix that multiplies the array response. So the difference is here in the presence of the inverse of Q. If the noise is white, the disturbance is white, Q is the identity matrix. So in the case the noise is white, the optimal clairvoyant beamformer coincides with the classical beamformer. So they coincide only if the disturbance is white. Otherwise, they are different. Now, this beamformer is sometimes called also a whitening matched filter. So WMF. So why whitening? Because the presence of the inverse of Q in practice can be interpreted as a whitening operation. So what do I mean with whitening? Whitening is synonymous of decorrelation. So let's try to understand this important fact, okay? Because it's important to understand the relationship between the two. Remember, still we are comparing two beamformers that are not adaptive. So we will understand later how to make them adaptive. But before doing that, I want to highlight the differences and the relationship between the classical beamformer and the optimal clairvoyant beamformer. So the output of the optimal beamformer is H optimal Hermitian Y. So it is this quantity Hermitian Y. Now you can express the inverse of Q, you can factorize as the product of its square root times its square root. I mean, we can define the square root of a matrix. I don't know if you are familiar with this notation, but it's possible to factorize a matrix as the product of its square root times its square root. So Q elevated to minus 1 over 2 times Q elevated to minus 1 over 2. And then we have to calculate the Hermitian. We calculate the Hermitian of this, so we get A Hermitian. Now, when we calculate the Hermitian, Q is an Hermitian matrix. So this Hermitian operation actually is irrelevant. You can remove. Then you can put these two terms together, the first two together, and you can express in this way as the square root of the inverse of Q times A Hermitian, and then you put these two together. For example,
Sir, you're not audible.
what happened? I mean, the connection went down.
Sir, now you're audible, but your screen is not visible.
I think the connection went down.
Now the screen is visible, sir.
So, but did you see my comments on this? So what did you miss?
So we have seen it, sir. We
Sorry,
have seen this slide.
I cannot hear you well. Can you repeat, please?
So we have seen this slide. We haven't seen the next slide.
Okay, okay.
Yeah, this one we haven't seen.
So I want to, so I will comment again this. So I want to explain why this optimal clairvoyant beamformer is typically called whitening matched filter. Now, without the Q, it's the matched filter. So it's obvious that the presence of the inverse of Q is the part that makes the whitening. So what do I mean for whitening? I mean that the presence of the inverse of Q is responsible for a whitening of the disturbance. Let's see why. So we start from the definition of the output of the optimal beamformer, which is H optimal Hermitian Y. Then I write explicitly the structure of the optimal beamformer. Then I factorize the inverse of Q as the square root times the square root. This is possible also for a matrix. It's a factorization that can be done in MATLAB just with the command sqrt. Then we calculate the Hermitian. So we get A Hermitian, the Hermitian of Q to minus 1 over 2 times the same times Y. Now, ideally, you can put together the first two matrices, the first two terms, and you can write Q to 1 over 2A Hermitian that multiplies the last two terms, Q to minus 1 over 2Y, and because any covariance matrix is Hermitian, Q is Hermitian, and the inverse of Q is Hermitian. So the Hermitian operation is ineffective on Q. Now, if you call this term here A tilde, and you call this term here Y tilde, you can express the output of the optimal beamformer in this way. And this is nothing but the classical beamformer with the impulse response matched not to A, but to A tilde, applied not to the original data Y, but to the transformed data Y tilde. And I mean, what are these transformed data Y tilde? First of all, you can notice that this is a linear transformation. So we take our original data vector and we pre-multiply by this matrix. So it's a linear transformation. So for example, if the data are Gaussian, the data remains Gaussian after this linear transformation because Gaussianity is preserved by linear transformation. So what I want to say is that applying the optimal beamformer is equivalent to the cascade of these two operations. First, we take our original data, Y, and we perform this linear transformation. We obtain the transformed data vector Y tilde, and then what we do with Y tilde, we apply on Y tilde a classical beamformer, but the classical beamformer is not matched to A, but is matched to A tilde. A tilde is what? Is the same linear transformation performed on the data, but applied to the array response. So it is like we have a new array response obtained by doing this linear transformation that we have done also on the data. Now, why this linear transformation is defined to be a whitening transformation? Whitening means, you remember, if you whiten the data, you just decorrelate the data. So whitening is synonymous of decorrelation. This can be proved very simply. So what happens to our data when we multiply by this? Obviously, there is the signal and the disturbance. So when we multiply the data by this, we get the signal, and the signal can be written as A tilde times Sn. So it is like if we have a new array, a different array with a different array response called A tilde, plus the transformed disturbance that I call W tilde, which is the same matrix multiplied by Q. So why this transformation, this linear transformation is called whitening, is called decorrelation? Because if you calculate the correlation matrix of the data, so of Y tilde, what is the correlation matrix of this? Okay, you take this and you plug here. So instead of Y tilde, you put this, and it's Hermitian. Then, because Q is deterministic, you bring outside the expectation. So the expectation operates on Y Hermitian. By definition, this is Ry. Ry has this structure here. So then you do the two multiplication. So you have the signal and the disturbance. So this one is nothing but A tilde is Hermitian. So what happened to the disturbance? So you have Q to minus 1 over 2 times Q that multiplies minus 1 over 2 because, I mean, the Hermitian is irrelevant. Now, if you factorize Q as the square root of Q times the square root of Q, you immediately see that the product of the first two is the identity matrix. The product of the last two, again, is the identity matrix. And so at the end, the correlation matrix of the noise is proportional to the identity matrix. And so it means that after this linear transformation, basically we have whitened the data. Because after this linear transformation, the correlation matrix of the noise is the identity matrix. So what we have done through this linear transformation is we have decorrelated the disturbance samples. So we have whitened the data. So this is a linear whitening transformation. So in other words, the optimal beamformer can be interpreted as the cascade of two operations. The first one is a whitening transformation. When you whiten the data, you change also the array response. And the array response of the whitened data is A tilde. And the second step is a matched filter, but matched to the transformed array response. So in other words, the output of the optimal beamformer can be interpreted as the cascade of these two linear filters. The first one is a whitening filter. So if the disturbance is correlated, the first things that we do is we whiten the data. Once we have, we whiten the disturbance. Once we have whitened the disturbance, we do the best thing that we can do in white disturbance. So we apply a matched filter. But the matched filter cannot be matched to the original array response because the array response has been modified by this whitening transformation. So the matched filter should be matched to the modified array response. But what is important to understand is that the optimal clairvoyant beamformer is different from the classical beamformer. Why? Because the classical beamformer is just a matched filter. But this is optimal only if the disturbance is white. If the disturbance is not white, the optimal thing to do is first we whiten the data and then we do matched filtering. In this way, we achieve a larger array gain. So we achieve the optimal, the best possible output signal to noise ratio. We can compare the optimal beamformer with the classical beamformer, also comparing the beam pattern. Okay, I think we can have the long break now, and then we continue from here. So I repeat, I want to stress very well what are the differences between the classical beamformer, which is a non-adaptive beamformer, which is optimal only in white disturbance, and the optimal clairvoyant beamformer, which is the optimal both from the point of view of the minimization of mean-square error and the maximization of the signal-to-noise ratio. And this optimal beamformer can be interpreted as the cascade of a whitening filter and the matched filter. The two beamformers coincide only if the disturbance is white. Otherwise, they are different, and obviously the performance of the optimal clairvoyant beamformer are better. The problem is that we don't know in general Q, or we don't know R Y, so we cannot implement in practice the clairvoyant beamformer. It can be implemented only in an adaptive manner, and